Ever wondered how a simple joystick lets you move a character with pixel-perfect precision, smoothly aiming, accelerating, and stopping exactly where you want? Today on Knowledge Hub, we're breaking down how a joystick works and why it can be so incredibly precise. At its core, a joystick converts physical motion into electrical signals, starting with the stick mounted on a gimbal or pivot mechanism that allows movement along two perpendicular axes, X for left-right and Y for up-down, while carefully controlling friction and return force using springs to ensure the stick always snaps back to its neutral center position. In traditional analog joysticks, each axis is connected to a potentiometer, a variable resistor, where pushing the stick rotates a wiper along a resistive track, changing resistance and therefore the output voltage. This voltage is continuously variable, meaning the system doesn't just detect direction, but exact position, so a slight tilt produces a small voltage change and a full tilt produces a larger one. The controller's analog to digital converter then samples this voltage, often at resolutions of 8 to 12 bits or higher, translating it into hundreds or even thousands of discrete position values. Modern controllers push precision further by replacing potentiometers with Hall-effect sensors, where a magnet attached to the joystick moves relative to a fixed sensor, allowing the system to measure position based on changes in a magnetic field. Because there is no physical contact, this eliminates mechanical wear, reduces electrical noise, and prevents issues like stick drift over time. But hardware alone isn't enough. Inside the controller, a microcontroller continuously samples joystick data very high rates, applies low-pass filtering to remove micro-vibrations from your hand, and defines dead zones around the center to ignore tiny unintentional movements. Beyond that, software applies response curves, often non-linear, so that movements near the center are extremely fine and controlled, while movements toward the edge ramp up speed more aggressively, which is why aiming slowly feels precise, but turning quickly still feels responsive. Game engines then layer additional logic on top, combining joystick input with frame timing, physics calculations, and camera smoothing to ensure consistency across different frame rates. Calibration routines further compensate for manufacturing tolerances, sensor offsets, and temperature changes, ensuring that every joystick behaves predictably. So the next time you gently tilt or fully push a joystick, remember, every tiny movement you make is being measured by sensors, converted into digital data, filtered, corrected, and mapped through software curves in real time, all within just a few milliseconds. If you enjoyed this deep dive into how joysticks achieve such incredible precision, make sure you subscribe to Knowledge Hub for more fascinating explanations of the technology you use every day. And as always, stay curious.